Welcome to this first video of my playlist about the best methods to convert amides into ketones. Amides are less electrophilic than esters, but the intermediate hemiaminals formed upon reaction with carbon nucleophiles are often more stable than hemiacetals. Thus, the formation of tertiary alcohols is sometimes less of a problem than with esters. This video is about the use of polar organometallics as nucleophiles, mostly organolithium and organomagnesium compounds. Numerous examples have been recently reported of the palladium-catalyzed addition of boronic acids to amides, but these reactions rarely offer advantages if compared to procedures with the more traditional reagents. Therefore, I won't discuss these palladium-catalyzed reactions here. In the other two parts of this playlist, we'll have a look at ionic enolates and at the conversion of amides into ketones under acidic reaction conditions. When polar organometallics add to carbonyl groups, the electrophilicity of the carbonyl group is first enhanced by coordination to the metal. Then the nucleophilic addition of the alkyl or aryl group occurs, followed by elimination of the metal amide. Depending on the amine, these can be very basic and do not form as readily as alkoxides. Therefore, the initially formed metallated hemiaminals can be quite stable, what may prevent the formation of tertiary alcohols. If the hemiaminal eliminates the metal amide, a tertiary alcohol can be formed by addition of the polar organometallic to the newly formed ketone. Alternatively, the metal amide can metallate the ketone and thereby protect it from further nucleophilic additions. Acidic starting amides may, however, also be deprotonated or dealkylated by the organometallic reagent. Dealkylation is rare because carbon-nitrogen bonds are strong and hardly polarized, but deprotonation can easily occur and lead to low conversions. One way to prevent the formation of tertiary alcohols is by further stabilizing the initially formed metallated hemiaminal. In the case of Weinrepp amides or amides containing additional heteroatoms, chelate formation can provide such additional stabilization. Alternatively, the nucleophilic addition may be conducted in the presence of silylating reagents or Lewis acids such as boron trihalides. With non-enolizable starting amides, some strong base may also be added to the reaction mixture to convert the newly formed ketone into an enolate. Highly reactive electron-deficient amides will react faster with the nucleophile and compete more effectively with any ketone for the nucleophile. Amides of strongly acidic electron-deficient acids will also yield more stable hemiaminals because the resulting ketones will also be electron-deficient, with a high tendency to form stable hydrates or hemiaminals. More reactive amides should also allow for lower reaction temperatures, what may also help to prevent fragmentation of the metallated hemiaminal. Organocerium, chromium or lanthanum compounds are less basic than organolithium or magnesium compounds and cause less metallation of the starting amide and yield more stable hemiaminals. Unfortunately, stoichiometric amounts of these metals are usually required. If a given dialkyl amide cannot be transformed into a ketone in high yield, some promising alternatives are imides, that is, NN-diacylamines, Weinrepp amides, morpholites, nitriles, the salts of carboxylic acids, anhydrides or acyl halides. Some of these are discussed in other playlists on this channel. Let's check some specific examples. Primary amides, such as the starting material of this example, will be quickly deprotonated by polar organometallics and thus require an excess of nucleophile. The intermediate hemiaminals seem to be quite stable, and a high yield of ketone was obtained here. Morpholine is less basic than piperidine or dimethylamine, and morpholites therefore more electrophilic than other amides. Despite the excess of Grignard reagent, a high yield of ketone resulted at 0 degrees Celsius, together with a small amount of tertiary alcohol. Morpholites seem to be almost as well suited as Weinrepp amides for the preparation of ketones. Their lower cost and toxicity if compared to Weinrepp amides increase their attractiveness even further. In this example, a metallated thiazole was added to a slight excess of chloroacetyl morpholine, again at 0 degrees Celsius. No alkylation, but mostly acylation occurred, and a reasonable yield of ketone was obtained. Amides containing electron-deficient alkenes may also react as Michael acceptors, in particular in the presence of traces of late transition metals. Early transition metals do not, however, catalyze Michael additions because these are too hard and form strong bonds to oxygen. Here, an excess of butyllithium was transmetallated with cerium and then added to cinnamoyl morpholine at low temperature. Mostly the vinyl ketone was obtained. In this example, an alpha-beta unsaturated Weinreib amide was treated with a large excess of lithiated methyl chloride at low temperature and in the absence of any transition metals. Despite the ability of metallated haloalkanes to cyclopropanate CC double bonds, this did not happen here, and a high yield of chloromethyl ketone could be isolated. Amides containing additional oxygen, nitrogen or sulfur atoms in close proximity to the carbonyl group can often be converted into ketones in high yield, without any precautions to prevent alcohol formation. Here, for instance, treatment of an alpha-alkoxyamide with a slight excess of butyl magnesium bromide yielded mostly a butyl ketone. No excessively low temperature was required and only 4% of the tertiary alcohol was formed. Isopropyl lithium or isopropyl Grignard reagents are strong bases and are often used for metallation. In this example, though, a clean addition to the carbonyl group occurred. An isopropyl ketone was obtained in high yield and without racemization. Amides containing further electrophilic functional groups may not react selectively with strong nucleophiles. In this example, it was, however, possible to convert the amide into a ketone in high yield without any cleavage of the oxyrane. Enantiomerically pure ethanol amines, such as ephedrine, can be used as chiral auxiliaries. Acylated ethanolamines are relatively easy to hydrolyze because of intramolecular assistance by the hydroxyl group. As shown here, these amides can also be cleaved and converted into ketones cleanly by treatment with an excess of an organolithium compound. No extensive racemization occurred. I would not really categorize imidazolides as amides and have not included here any examples of their conversion into ketones. Imidazolides are more reactive than most esters and are often used as acylating reagents. Anyway, just one example here to show that also imidazolides can be suitable electrophiles for preparing ketones. Despite the huge excess of Grignard reagent, no alcohols were formed, probably also because the product was a sterically very crowded ketone. As catalyst, 10% of iron chloride was used to prevent reduction of the ketone by hydride transfer. I'll discuss the side reaction more thoroughly in a minute. Lactams are more reactive than open-chain amides and can also be converted into ketones, sometimes in high yields. In this example, a slight excess of methyl magnesium bromide at room temperature yielded a methyl ketone in 80% yield. With ethyl magnesium bromide, however, the yield was much lower, probably because of a partial reduction of the ketone to an alcohol by hydride transfer. If a given amide is too unreactive, forcing conditions may not be helpful because these would reduce the overall selectivity and increase the amount of tertiary alcohols and enolate formation. An alternative is the activation of amides by one additional acylation at nitrogen. Chloroformates or Bock anhydride are, for instance, often used to activate lactams, as in this example. Here, a pyroglutamic acid derivative had to be converted into a terz-butyl ketone. While terz-butyl magnesium chloride at room temperature led to extensive enolate formation, this could be suppressed by lowering the reaction temperature and by using an organocerium reagent. Here, a non-enolizable, sterically rather crowded lactam was treated at low temperature with a large excess of methyl lithium. The high yield of ketone was probably due to the stability of the hemiaminal and the poor sterical accessibility. One common transformation is the conversion of polar organometallics into aldehydes by treatment with an excess of DMF. This works so well because formamides are highly reactive for electronic and steric reasons and are finished reacting with any nucleophile before fragmentation of the hemiacetal can occur. In this example, a slight excess of N-formylpiperidine was added to a dilithiated bromothiophene at low temperature and a good yield of dialdehyde resulted. Unfortunately, lithiated haloarenes, as the intermediate here, are treacherous and can decompose violently even at low temperature. Somehow, nature always finds some mechanism to convert them into lithium bromide and charcoal. Scale-up of such intermediates is dangerous and should better be avoided. This example is an elegant strategy for the lithiation and formylation of a bromoarene in the presence of an enolizable amide. The latter was protected by deprotonation, and after bromine-lithium exchange with butyllithium, the lithiated arene was formulated with a slight excess of DMF. No substantial formylation of the amide occurred. So what are the most relevant side reactions? I have already discussed in depth tertiary alcohols and how to prevent their formation. One less known side reaction is the dehydration of primary amides to nitriles. With sterically demanding non-enolizable amides, this can become the main pathway, as in this example. Then, amides may also be metallated by polar organometallics at the nitrogen-bound alkyl group. Such reactions are difficult to predict, and one should always characterize the products of a reaction carefully. Here, for instance, NMR spectra of the actual product and that of the isomeric beta-ketoamide may look deceptively similar. I showed you some examples of the preparation of enones from alpha-beta unsaturated amides where no Michael addition occurred. Depending on the precise conditions, though, such additions can occur, even in the absence of transition metals. In this example, Michael addition became the main reaction pathway. Maybe the lithium alkoxide slowed down the nucleophilic addition to the carbonyl group sufficiently to allow the Michael addition to take hold. Polar organometallics with beta hydrogen are good hydride donors and can cause the reduction of the newly formed ketone. Here, the same imidazoline as in the previous imidazoline example was treated with an excess of sec-butyl magnesium chloride, and almost half of the ketone was reduced to a secondary alcohol. As I already showed you, this could be prevented by addition of a catalytic quantity of iron trichloride. On this and the next slide there are some further examples which you can also find in the description of this video. The next presentation is about the use of ionic enolates as nucleophiles. These are usually not nucleophilic enough to react with simple amides, but there are some exceptions. See you then.